Let's embark together on a visual journey through space and time. We find ourselves in the vast expanse of intergalactic space, billions upon billions of kilometers from Earth, lost between two neighboring galaxies. Our own, the Milky Way, and Andromeda, another galaxy composed of hundreds of billions of stars. The space around us is almost perfectly empty, but we are not in nothingness. There is a web woven around us. It is the fabric of the universe itself, SpaceTime. This imaginary grid, composed of countless particles, allows us to visualize the invisible, to understand the geometry and dynamics of the universe. From our vantage point, the grid is calm, motionless, undisturbed. If we were to throw a marble, it would travel straight ahead, forever moving away through the void. However, the grid is not entirely static. If we fast forward, we see it drifting very slightly, like a river that flows through the stars, carrying everything with it. The stars, clouds of gas, and dark matter all distort space-time, pulling the fabric of the universe in their direction. As this happens, the two galaxies, the Milky Way and Andromeda, are slowly drawing closer. In several billion years, long after we are gone, the two will merge and become one. At the same time, we now know that most galaxies are moving away from one another as the universe expands. Space itself stretches, and galaxies are carried farther apart. As this expansion continues, the wavelength of their light elongates, shifting it towards the red end of the spectrum. This expansion accelerates due to the still mysterious force of dark energy. The expansion began 13.8 billion years ago in an extremely compressed state, containing only a fluctuating energy. Suddenly, the universe expanded rapidly, reaching astronomical dimensions in a fraction of a second, a phenomenon known as the Big Bang. What existed before that remains a mystery. Tiny fluctuations in energy attracted matter, which condensed into filaments, halos, galaxies, and eventually stars. Today, we live near one such star, the Sun. Around it, a system of planets, asteroids, and comets move freely through the grid of the universe. The immense mass of the Sun curves space-time, and the fabric of space itself falls towards the star, pulling everything with it. This is how the planets stay in orbit, always moving forward but continuously pulled back towards the Sun. Planets also distort the grid in their own way. Earth, for example, holds the Moon, its natural satellite, and all our artificial satellites in orbit. As objects move in space-time, they are influenced by its curvature. The International Space Station, for example, moves straight ahead through space-time, but its motion is subtly altered by the Earth's curvature. At greater distances, objects can escape the pull of gravity, but as they approach the source of gravity, the curvature accelerates and the pull becomes stronger. When we launch a rocket from Earth, it must reach an extremely high speed to escape the gravitational pull. At the surface, space-time converges towards the center of the planet, and if we drop several apples, the fabric of space-time will bring them together, stretching them apart in the opposite direction. These tidal forces caused by the Moon result in the ebb and flow of Earth's oceans. The Earth also rotates on its axis, completing one full rotation approximately every 24 hours. This motion influences space-time very slightly, dragging the grid along with it. If we were to drop an apple, even though it might not touch the Earth, its trajectory would be slightly bent by the Earth's rotation. Inside Earth, the grid continues to fall towards the center, but the materials making up the planet resist this collapse. The outward pressure they exert prevents the planet from collapsing inward. It is this resistance that we feel in our legs when we jump and land back on the ground. In about 5 billion years, the Sun will exhaust its fuel and begin to die. It will no longer be able to generate the pressure needed to resist the flow of space-time, causing its core to collapse. This will form a white dwarf, and its outer layers will expand into a planetary nebula. Some stars, however, meet a more violent end. A supergiant star, 20 times more massive than the Sun, will collapse in on itself and explode as a supernova. Its core will shrink into a neutron star, a dense object that warps space-time so strongly that even light is dragged along with it, creating strange optical effects. In some cases, stars become so massive that their cores collapse beyond the neutron star stage, forming black holes. These black holes create such intense curvatures in space-time that nothing, not even light, can escape. Anything that falls into the black hole is carried downwards at speeds faster than light, entering a region known as the event horizon, from which no signal can escape. The immense gravitational pull of a black hole also attracts nearby stars and matter, which form an accretion disk around it. In certain situations, two black holes converge, creating a larger black hole and emitting powerful gravitational waves, ripples in the fabric of space-time itself. These waves travel outward at the speed of light, distorting everything in their path. On September 14, 2015, one such wave was detected by researchers, marking the first direct observation of gravitational waves and opening up a new field of astronomy, gravitational wave astronomy. Through this, we can begin to probe the very structure of the universe itself.